Hello to everyone. Welcome to the course on numerical linear algebra applications. Today we are going to learn lecture 5. In continuation to the previous lecture that where we started with Gaussian elimination with partial pivoting. We have already seen the advantage of partial pivoting to find out a solution to the linear system, that is Ax is equal to B. Ax is equal to B, linear system. Well, today we would see what are the ways and means of the complete pivoting and how it motivates us to go to the complete pivoting in compared to the partial pivoting. So let us start with P comma Q. They are all non-singular matrices. Non-singular matrices. P and Q are two non-singular matrices such that PAQ is equal to LU, where L is the lower triangular matrix, and U is the upper triangular matrix. Lower triangular matrix and upper triangular matrix. So we started with PAQ is equal to LU. Right? Now set AN minus 1 is equal to U, upper triangular matrix. We define a series of matrices Q1, Q2, Q3, Qn minus 1, which I call it as a Q. Similarly, Pn minus 1, Pn minus 2, P1, which I call it as a P. See that difference here? Q matrix will be started from Q1, Q2, Q3, Qn minus 1, whereas P is Pn minus 1, Pn minus 2, Pn minus 3, Pn minus 4 up to 1. That is, keep on decreasing and here keep on increasing. And L is the lower triangular matrix. The matrix P acting on M minus 1, the matrix P acting on M minus 1, the matrix P acting on M minus 1, P minus 1, M1, P1, raised to the power minus 1, and PAQ is equal to L of U. PAQ is equal to L of U. And set AN minus 1 is equal to U. And we define Q1, Q2, Q3, Qn minus 1, P as Pn minus 1, Pn minus 2, P1. And this L is equal to P times of M minus 1, P minus 1, P minus 2, M1P whole power minus 1. And PAQ is equal to L of U, where P and Q are non-singular matrices. P and Q are non-singular matrices. L is the lower triangular matrix and U is the upper triangular matrix. Now, with this algorithm, we could able to see that how the complete pivoting will be carried out. So, Gaussian elimination with complete pivoting at the kth step, that is at the kth step, the search for the pivot is made among all the entries of the submatrix below the first k minus 1th row. Right? We carry out among all the entries of the submatrix below the first k minus 1th row, that is k minus 1th row, identify the largest element in magnitude among all the elements of the submatrix obtained by deleting the first k minus 1 rows and k minus 1 columns. That means you delete the particular row, k minus 1th row as well as k minus 1th column. Right? That is the basic algorithm of the Gaussian elimination with complete pivoting. That means essentially what you are trying to do is, whatever you do it Gaussian elimination with partial pivoting for the rows, you also do handle for the columns so that the complete pivoting will be taken care. Now we see this example for the matrix A is equal to, let's say, 0, 1, 1, 1, 2, 3, 1, 1, 1. So it is a 3 by 3 matrix. 3 by 3 matrix. So K is equal to 1. The pivot element is 3 here. the pivot element is 3. Okay, and row is second row and column is third. So this is the one, the pivoting element, the maximum element. So the k is equal to 1, the pivot element is 3, right? This is the maximum element in absolute value, and this is occurring in second row, third column. So r is equal to 2, c is equal to 3. Okay, now let us see interchange r2 r3. How do I bring this maximum element as a pivotal element? That means it should come either in 1 by 1, or it should come in 2 by 2, or it should come in 3 by 3. That means it should be on the main diagonal, essentially. It should be on the main diagonal, essentially. So what we can do with this is, we interchange R2 as R3 and R3 as R2. Well, then interchange C1 as C3 and C3 as C1. That means C1 will be going to the place C3. So instead of C3 you do have C1. Okay. So that means C1 will go to the C3 and C3 will go to C1. Right? So with that, what happens is, you do get what you call, this is the matrix 3 by 3. So that means A11 is not equal to 0 is the maximum element. Maximum element. So which we brought it as pivotal element. If you look at into this matrix, you see already we pointed out that this is the maximum element matrix. So this, what I did was, I did the second row as third row and third row as second row, and at the same time the C1 will be replaced by C3 and vice versa. So with this I could able to get this matrix 3 2 1 1 1 0 and 1 1 1. So obviously with this element, the transformation, that is by rows plus columns, I could able to bring the maximum element in the 1 by 1 position. So that is why it is called a complete pivoting. So therefore you do bring the maximum element in the following fashion. Let us go ahead. Now perform the Gaussian elimination. So R2 would be, that is R2 minus 1 by 3 R1. So this is the multiplier. That is the multiplier. M31 is minus 1 by 3. And R3 would be shifted to minus 1 by 3 R1. So M31 is also multiplier. This is M31. So this is equal to. So that means essentially you do have M31 is equal to minus 1 over 3. So with this, these two elements have become zeros, and this would remain as it is. Right? So the A11 is equal to 3 should be free from 0. Right? And below that all will be zeros. So this process should help us in order to bring the lower triangular matrix and upper triangular matrix. Well, that is for k is equal to 1. When k is equal to 2, you look at here, the pivot is 2 by 3. So among the existing, this is the bigger one. So how do you bring this as the 2 by 2 element? That means I wanted to have A22 is equal to 2 by 3. I want to bring it. So what I do is R3, that is R3 is equal to the R3 is, so pivot entry is 2 by 3. So R2 is, this is 2 and column is 3. So R2 I would change as R2 R3 I will change it. So R2 I3 I will change it. So it becomes 1 by 3 and minus 1 by 3. Right? 1 by 3 minus 1 by 3, and this will become 1 over 2 by 3 and minus 1 by 3. So or else you can straight away change this as the columns. These two columns you can change it. 1 2 by 3 minus 1 by 3, 2 1 by 3 1 by 3. So simply you can use this so that the 2 by 3 element has come up. So this is the 2 by 2 element, that is A22 is equal to 2 over 3, which is free from 0. You could able to get it. Right? Well, in this process we could able to do K1 is equal to 1 comma 2. So now so look at this. So M32 is equal in this process. This is 1 by 2. So you could able to get this matrix. This is the non-leading diagonal element, and these are all zeros and these are all non-zeros. So you should be able to get what you call the upper triangular matrix. This is the upper triangular matrix. Now, we using these multipliers, as I spoke, we could able to write this as lower triangular matrix. Lower triangular matrix, I could able to get it. So therefore, this is the main diagonal and these things will be zeros and these are all non-zeros. So this is L and this is U. So you could able to obtain both lower triangular matrix and upper triangular matrix in this process. Right? Now, for P, so what is the P matrix? So the P matrix which you have chosen, same kind of operations I will do it. 1 0 0 0 1 0 0 0 1. R2 R3. So R2 R3, I will keep the R1 as it is. R2 R3 will be 0 0 1 0 1 0. Okay. So if I do R2 R3 1 0 0, then again this is 0 1 0 0 0 1. So we have the matrix, whatever matrix we have done, for the matrix whatever we have operated earlier, same thing we will be operating. So R2 R3 we did it, again R2 R3 as we did it previously. So therefore ultimately I would be able to get 1 0 0 0 1 0 0 0 1. So we have a P matrix. If you do this matrix, this is actually I3 matrix. So determinant of P is free from 0. So therefore P is a non-singular matrix. Is a non-singular matrix. P is a non-singular matrix. So we should be able to obtain the non-singular matrix P in such a way that the determinant of P is equal to not equal to 0. Right? So that's how we could able to apply the complete pivoting for this matrix 3 by 3. Okay, for Q, let's say same Q. So whatever we did it for Q, instead of rows, we should do for the columns. So for the matrix Q, right? For the matrix Q, we have a 1 0 0, 0 1 0 and 0 0 1. So whatever column operation we did it, C1 to C3. I did that. That means 0 0 1, that is this is actually C3 replaced by C1. 0 1 0 will remain as it is, as it is, as it is. This is 1 0 0 is the matrix C3. Okay, C3 will be, this is the matrix, C3 is nothing but the C1 of the matrix. So again what I do is C2 C3. C2 C3 is 1 will remain as it is, this will remain as it is. Yes, now let's look at into this column. So 1 0 0, 0 1 0, 0 0 1. So this matrix, if you apply C1 and C3, so it becomes like this: 0 0 1, 0 1 0, 1 0 0. And when you interchange C2 C3, it becomes 0 1 0, 0 0 1, 1 0 0. So therefore, essentially the matrix Q has become 0 1 0, 0 0 1, 1 0 0. This is the matrix Q. So if you find the determinant of this matrix, you see here, this is actually 0. Right? This is actually 0. So the determinant of this matrix is 0 1 0, 0 0 1, 1 0 0. So therefore, when you apply this matrix Q, so this turns out to be 0 0. So therefore P is equal to, you have got 1 0 0, 0 1 0, 0 0 1. That is the Q. And this is the matrix Q. Right? So Q is 0 1 0, 0 0 1, 1 0 0. So in the main diagonal, all entries are actually zeros. Right? In the main diagonal, all entries are zeros. Okay. Now we can verify, very quickly we can verify what would happen to the matrix PAQ. So if you multiply this matrix PAQ, P is 1 0 0 and 0 1 0, 0 0 1, that is P. and coefficient matrix is, that is the coefficient matrix is 0, 1, 1, 1, 2, 3 and 1, 1, 1. That is the coefficient matrix. And Q is 0, 1, 0, 0, 0, 1, 1, 0, 0. So therefore, you get the LU matrix. LU matrix as, so that is the LU matrix you do get as the matrix like this, that is 3, 1, 2 and it is 1, 1, 1 and it is 1, 0, 1. That is the matrix 3, you do get it. So that means essentially you have obtained two matrices P and Q in such a way that the P and Q are non-singular matrices. Okay, that's how you do get matrices, the P and Q, in such a way that the PAQ will be equivalent to L into U. Now let us see the growth factor. How do you obtain the growth factor? Now to obtain this growth factor, you see the growth factor over here. Rho is the ratio of the largest element of A, that is A of 1 and A of 2, like that you do have A of n minus 1 to the largest element. Largest element in magnitude. Largest element in magnitude of A. So rho is equal to maximum of alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, etc. alpha n minus 1 divided by alpha, where alpha is nothing but maximum of Aij, right? And alpha k is maximum of Aij, the kth row. So this is the kth row and ijth element. So that's how we do compute what you call the growth factor. Now let us look at into the simple example how we can able to find out the growth factor. Look at this. This is the matrix, you do have it, right? Look at this. A11 is very small, and A21 comma A12 comma A22 relatively bigger. That means these elements are actually relatively bigger and compared to the element A21, A12, A13, right? Now let's see what would happen to the Gaussian elimination without pivoting. So if you do Gaussian elimination without pivoting, A of 1, that is nothing but capital U, that is 0, 0, 0, 1, 1, 0 and it is minus 10 power 4. You see that this is a very big element if you take absolute value, and this is a very small element. So maximum of first row A1 of Ij, this is equal to 10 power 4. Maximum of Aij is equal to 1. And rho is the growth factor. I do compute the growth factor as the absolute value 10 power 4 upon the other row element is 1, maximum element. So which is equal to 10 power 4. So high leads to unstable. That means whenever the growth factor will give you how actually you can find out the stability of the solutions. So therefore we compute over here rho. Obviously this system is unstable system. So unstable system. So the conclusion is Gaussian elimination without pivoting gives unstable system. So the matrix is 0, 0, 1, 1, 1, 0, 0, 1 and 1. So we compute the growth factor A of 1, U is equal to this thing, and we find out the growth factor. So growth factor is the maximum, so almost close the 10 power 4. So high growth factor will lead to unstable system. So therefore very much necessary to look into the what do you call the pivoting. Now let us see the Gaussian elimination with partial pivoting. Let's say partial pivoting. That means we do only row wise. So what would happen to this system? So we do A of 1 is equal to U, that is equal to 1, 1, 0, 1. Right? Okay. Maximum of Aij of 1, that is equal to 1, and maximum of Aij, that is equal to 1. So therefore the growth factor rho is equal to 1. So therefore small growth factor leads to what you call a stable system. So therefore partial pivoting leads to a stable system. Okay, partial pivoting leads to a stable system. So therefore, Gaussian elimination with partial pivoting leads to a stable system. So we could able to obtain the solution by using the Gaussian elimination. So it is very clear from these this example how Gaussian, if you start with directly the solution without pivoting, it will lead to an unstable system. It is not a desirable case. So, but Gaussian elimination with partial pivoting will leads to a stable system, and you do get a best approximation. Now you see another example. Look at this example. 4 by 4 matrix. Now 4 by 4 matrix, you see first row is 1 0 0 1, second row minus 1 1 0 1, third row minus 1 1 1, fourth row minus 1 1 1. So either you have a ones or zeros. 1 means plus or minus 1. Very typical example. Let's see what is the growth factor. The growth factor, maximum all elements A3. So maximum of all elements in A3. So what is the maximum elements of all in A3? So if you compute this maximum element by using the previous formula, that is the one which we did it over here defined, maximum of alpha 1, alpha 2, alpha 3, where alpha is equal to maximum of mod of Aij. So if you use this, it turns out to be what we call the value. This is the value which you get it, right? So this value you would get maximum element in A, that is 1. So 8 by 1 is 2 cube. So 2 cube is 2 power n minus 1. So growth factor is the 2 cube, that is 8. That is in compared to 10 power 4, it is a smaller value. So therefore, so what is the conclusion is, for Gaussian elimination with partial pivoting, that is growth factor rho is less than or equal to 2 power n minus 1, where n is the size of the matrix, right? So for Gaussian elimination with partial pivoting, rho is less than or equal to 2 raised to power n minus 1, and n is the size of the matrix. That is maximum of number of rows or columns. Maximum of number of rows or the columns. That's what the matrix which will give you. The elements of the reduced matrix AK very often continue to decrease in size. We see that quite often we see the elements of the reduced matrix AK is very often continue to decrease in size. And another observation which we can see is, therefore, Gaussian elimination with partial pivoting is not unconditionally stable. In theory, in practice, it is considered to be a stable algorithm. So it is a stable algorithm. Because when you do the Gaussian elimination with partial pivoting, you could able to get the nice solution, and which we call it as a best approximation. So this is a desirable case. Desirable. Which is a desirable. So therefore, the idea is Gaussian elimination with partial pivoting is unconditionally stable in theory, but when it comes to the practice, it is considered to be a stable algorithm. So it is a stable algorithm. It is a stable algorithm. So we wanted to have a stable algorithm. Whatever we do it, the algorithm should be a stable algorithm so that we get the best approximation. Well, let us move ahead. Head mode matrix. You see here, an n by n matrix such that its elements are plus or minus 1, right? And h times of h transpose is n factorial over here. Look at here, this is n factorial. So in the previous matrix, if you look at very closely here, all the elements of this matrix are either 1 or 0 or minus 1, right? So now if you look at this n by n matrix, all elements are either plus or minus 1, okay, apart from 0. So now we will make a conclusion over this remark. And LU factorization of a matrix A does not always exist. So therefore, it is not necessary that you do have a LU factorization. LU factorization need not exist all the time. LU factorization need not exist all the time. If the leading principal minors of A, if the leading principal minors of A are all different from 0, if the leading principal minors of A are all different from 0, then the LU factorization of A exists and is unique. Right? If the leading principal minors of A, are all different from 0, then the LU factorization exists and it is unique. Right? So if the leading principal, that means the previous case which you have seen, leading principal we computed are all different from 0, then we ensure that the LU factorization exists, and the so-called LU factorization is a unique factorization from over here. Now let us move ahead and make some conclusions. Aspects of stability, instability, and practical stability in terms of growth factor of the Gaussian elimination scheme. You see here, see that you always wanted to design a stable algorithm. If the algorithm is unstable, then it is of no use. So we wanted to have a stable algorithm. Gaussian elimination without pivoting is unstable. As we already seen that if you don't do the Gaussian elimination without pivoting, it leads to a unstable system in general. Gaussian elimination with partial pivoting is stable in practice. So if you do the Gaussian elimination stability, that is partial pivoting, it is stable in practice. Gaussian elimination with complete pivoting is stable. So that means complete pivoting means we do handle both rows as well as the columns. So obviously when the partial pivoting is stable, so when you do the column, it is obviously a stable algorithm. So essentially the conclusion is Gaussian elimination with partial pivoting will lead to a stable algorithm, which is the desirable process. Well, now let us look at into the what is the flop count, number of floating point operations, number of floating points per second. What are the number of floating points per second? So A is equal to L into U, that is lower triangular matrix, upper triangular matrix. Method is without pivoting. This is without pivoting. And flop count is 2n cube by 3. That is the flop counting. And stability is unstable in general. So the method will become unstable in general. Right? And if you write this matrix PA is equal to L into U, Gaussian elimination with partial pivoting, that is 2n cube by 3 plus big O of n square, stable in practice. And similarly, PA cube is LQ, Gaussian elimination with computing pivoting, 2n cube by 3 order of n cube, stable algorithm. So that means complete Gaussian elimination with complete pivoting leads to a stable algorithm. Gaussian elimination with partial pivoting leads to a stable algorithm in practice. So there is a difference between these two things. So that means complete pivoting always leads to a stable algorithm, whereas partial pivoting leads to stable in practice. So if you don't do the pivoting, obviously you do get what you call the unstable algorithm. Let us move ahead. Now let us again go back to the linear systems. The system Ax is equal to B is consistent, we can call it as a, that means there exists a solution if and only if rank of A is equal to rank of the augmented matrix. This is the augmented matrix. Suppose if A is the matrix Aij m by n, the augmented matrix is nothing but augmented matrix A of is nothing but Aij m into n, then rest will be what you call the columns, the right side vector, right? Maybe zeros or non-zeros or whatever. That's what we call it as the augmented matrix. So if the system Ax is equal to B is consistent if and only if the rank of A is equal to rank of the augmented matrix. If the system is consistent and the columns of A are linearly independent, then the solution is unique, right? So that means to have a solution Ax is equal to B, the rank of A should be equivalent to rank of the augmented matrix. Then we say that it is a consistent system. And if the system is consistent, there is a solution and the columns of A are linearly independent, then the solution is unique. right? And the columns of A are linearly independent. If the system is consistent and the columns of A are not linearly independent, then the system has infinite number of solutions, right? So for consistent solution, that means you do have a solution whether it is unique or you have an infinite number of solutions, right? And if the consistent system, number of columns of the columns of A are linearly independent, right? Linearly independent, then you can say that the system has a unique solution. And they are linearly dependent, then you can say that it has infinity number of solutions from this concept what we learned. Now let us go further. Some applications, where you get some applications over here. An electrical circuit problem by famous Kirchhoff's current flow, all of you knowing very well Kirchhoff's current law, is an algebraic sum of all currents entering a node must be 0. That means the flow entering into the system should be same as the flow leaving into the system. So it is like a equilibrium, right? The whatever flow is entering into the system through there is flow of electrons, which we call it the current, will be same as the flow of electrons leaving the system. Algebraic sum of the entering into a system must be 0. So analysis of a processing plant consists of interconnected reactors. Now if you look at into the reactors, right? Reactors, nuclear reactors. So whatever the entering the property or the mechanism entering into the system should be same as the mechanism which is leaving into the system. So we do get quite often what we call the ordinary differential equations, that is mass spring system, ordinary differential equation, partial differential equation, temperature distribution system. So an example of ordinary differential equation is mass spring system, where the mass is elongated through a spring, right? Partial differential equation, temperature distribution. How the temperature will be distributed to different modes, that is conduction, convection, radiation. So when you talk about the solids, we do have the conduction. When you talk about the fluids, flow of electronics, then there is a convection. And in many cases, we also do have a radiation. So three different modes of transport of heat, that is the conduction, convection and radiation. So depending on the kind of situation, which is dominant and which is not dominant will be known. So well, a major objective in a heat transfer problem is to determine the temperature distribution, that is T of xyz, that means T of x, y, z, T of xyz. In a medium resulting from imposed boundary conditions on the surface of the medium, right? Once this temperature distribution is known, this temperature distribution is known, the heat transfer rate at any point. So temperature distribution is known, the heat transfer rate at any point in the medium on its surface may be computed by Fourier's law. So that means temperature is known, we can know the heat transfer. That means temperature distribution is the global set and heat transfer is the local set. That means if the heat transfer is, the temperature distribution is known, we can compute how much heat will be transferred. So therefore, the temperature distribution is, when the temperature distribution is known, the heat transfer at any point in the medium on its surface may be computed. That means, so once you know the temperature, then heat transfer can be computed and what is the mode of transportation and all. If you look at over here, the what you call Fourier law. So Q of x is equal to minus k times of dt by dx. So k is what is called constant, that is the conduction constant. Similarly, in the y direction, you see over here, minus k into dou d by dou y. Similarly, in the z direction, you see over here. So essentially, what is Q? Q is nothing but heat transfer rate. And Qx is nothing but heat transfer rate in the x direction. And dou d by dou x is temperature gradient in the x direction. And K is the positive constant, thermal conductivity of the material. So therefore, by knowing all these properties, we could able to find out how heat would be transferred from one mode to different mode, right? One mode to different mode. Now, if you look at this, the temperature distribution is known, that heat transfer rate at any point of the medium surface may be computed using the Fourier law. So once the temperature distribution is known, the heat transfer rate at any point we can compute by using the Fourier's law. And Fourier's law is this thing, as we spoke over here. This is the Fourier constant K, right? That's how we can compute the temperature distribution. Now let us look at into very simple important example. Consider a homogeneous medium in which temperature gradient exists. Let's say that the temperature gradient exists and the temperature distribution is T of xyz t, right? So as we spoken very well, the mode of transport it is conduction, convection, radiation. Conduction takes place in solid bodies. Convection is in flow through what is called the flow of the particles, right? And radiation is through what do you call the radioactive substance, right? Third mode of transport of heat. So different mode of transport will have a different applications. When you go to the imaging or topography, radiation will have a higher role. Similarly, when you go to solid bodies, you do have a conduction. When you go to fluids, you will have a convection dominant role. Now let us look at into the diffusion equation which governs this temperature distribution is obtained by applying conservation of energy over an infinitesimal element. Look at this conservation of energy. So what is this value? This is d by dx of k times of dt by dx. K is what is called thermal conductivity. Similarly over here in the y direction, this is dou y of k into dou t by dou y. Similarly over here, dou by dou z of k times of dou t by dou z, right? Well, plus z dot is equal to rho Cp into dou t by dou t. So rho is the density and Cp is the specific heat at constant pressure and dou t by dou t is the unsteady, that is temperature distribution with respect to time, right? So this is the equation which governs the diffusion energy. Suppose if K is a constant, then what would happen? So this will become what we call, if K is a constant, then it becomes d square t upon dx of 2 plus d square t upon dy of 2, d square t upon dz of 2. That is what we call a Laplacian operator. So this Laplacian operator will play vital role in many engineering applications. So look at here, that's what I wrote. When K is a constant, we do have this thing, Q dot by K is equal to 1 by alpha into dou T by dou T. So this is the temperature distribution with respect to time, which we call unsteady temperature. Unsteady temperature, where alpha is equal to the K by rho Cp. So that is thermal diffusion constant, which we call it as the thermal diffusivity, alpha. Well, moving ahead further, for steady case, what would happen is, that is dou t by dou t will happen to be a 0. So if that is the case, we will have this equation, that is dou square t by dou x square plus dou square t by dou a square, dou t square t by dou z square plus q dot k is equal to 0. If no energy generation q dot k is equal to 0, then simply we do have what we call Laplace equation. And if it is a two-dimensional case, we will have a dou square t by dou x square, dou square t by dou a square, which we call it as del square of t is equal to 0, Laplacian equation. So therefore, it is very important in order to find out how actually temperature distribution is known for a steady case and for two-dimensional case and so on and so forth. It's very interesting how the heat will be transferred. Let us look at into a very simple example. If the heat transfer is unsteady, change in energy storage, then what happens in one-dimensional case? Dou square t by dou x square is 1 by alpha into dou t by dou t, which is what we call a parabolic. How it is a parabolic? Its solution looks like in the parabola. So a well-known scheme for numerically solving PDE is finite differences. So what is the finite difference? Well-known scheme for solving PDEs is, we replace the differentials by difference coefficients and thereby the differential equation will be transformed into algebraic equations. Difference equations, algebraic equations. So the idea is to discretize the PDE by replacing the derivatives with their approximations. That is what we call finite differences. So that means when you replace this PDEs by finite differences, so we discretize PDE by replacing the derivatives, which we get into what we call a finite differences. This is the basic idea of solving the PDEs. So we can see some examples operators. You see dou square t by dou x of 2 evaluated at I comma j, dou x of 2. So that means t of I plus 1j minus t ij plus ti minus 1j upon delta x. What is delta x? Delta x is in the ith direction. Delta x is the spacing in x direction. Spacing in x direction. Similarly, we can write dou t's by dou y's of 2. That is evaluated y. So we can write like this. So that means the indices is when I is varying I plus 1, I and I minus 1. J is varying j plus 1, j minus 1. So for two-dimensional Laplace equation, if you substitute over here, what would happen is the scheme turns out to be like this. So you do get what you call T of I plus 1 j plus T of I j minus 1 plus T of I plus 1 j, T of I minus 1 j minus 4 T of I j is equal to 0. So the indices Tij is nothing but temperature distribution at Ij plus 1. This is the temperature distribution Ij minus 1. This is the temperature distribution I plus 1j. This is the temperature distribution I minus 1j. This is at T of I comma j. So that's how we could able to compute the discretized equations, right? Well, moving ahead further, solving a linear system with a multiple right hand side vector. Suppose if you have a more than one right vector or different right hand side vector, how do you need not have to do the from the scratch. So you can logically think the algorithm and how do you adopt the multiple right hand side. What is the input you do have? Input is the matrix A R n by n and the matrix B is equal to R of nm. Output we do expect is x belongs to R power nm such that Ax is equal to B. What is the step 1? Step 1 is Gaussian elimination with partial pivoting. That means P times of A is equal to L of U. Right? And solving M linear triangular systems, L of Zi is equal to P into Bi. Solving M upper triangular matrices, Uxi is equal to Zi and Pax4 will be x is equal to x1, x2, x3. This is the algorithm quite often we use when we have a multiple right hand side vector. So that means you don't need to scratch every time different multiple right vectors. You can adopt it and you can able to find out. Let's see that a simple example. I have a matrix A 1, 2, 4, 4, 5, 6, 7, 8, 9. See that multiple right hand side vector 1, 3, 1 and 2, 4, 6. So when I do this, so this is the you look at here. So I transformed this and I got into over here. This is the matrix I do get. So when I do the Gaussian elimination, the previous case, the way which I did it, I do end up with a lower triangle matrix. I do end up with the matrix called P. So further if I go ahead, solving true triangular matrix, I do get a matrix of L of Z1 is equal to B1, whereas Z1 is equal to this. So I should be able to apply the algorithm in either cases and get these two matrices L and P in such a way that they should be free from 0. And when you have a multiple right hand side vector, I could be able to get it. Similarly, you do get what you call U. You can get like this 5, 25, 7 and you do get the matrix like this. Ax is equal to B matrix. So therefore, essentially what you get is when you have the different right hand side vector, you do get a, what you call the solution is 1 by 3, 1 by 3, 0. And for second set, you do have, this is the matrix, what we get, it is and all. So that means this is the x1, that is 1 over 3, 1 over 3, 0. And this is, that is minus 2 over 3, 4 by 3 and 0. This is the vector, you do get it. So from today's lecture, what we learned is, we have learned Gaussian elimination with complete pivoting and stability of the algorithms and consistency of the algorithms, and if you have a multiple right hand sector, how to handle the systems arising in real applications. And we also have seen that Laplace equation and its variants. So I am sure that we would continue in the same process and you might have learned, and I will stop at this point of time. Thank you very much.